Okay, so this is like the fourth or fifth time of me doing this. I think I got it fixed and got all my technical difficulties out of the way. This is the fourth video in a four-video series about this fragility metric that I came up with in the final stages of my PhD last year. So wanted to talk about this final part where I talk about how to calculate this fragility metric and give some simulation results where I show a few ways why a few reasons why it's a good metric to potentially use. So it was back in January when I think I did video 3. So now it's April, but we're here now. Go ahead and finish off this series. So, all right, still having a couple of difficulties, but okay. So this is the planar robot, and there are a couple of things to keep in mind here. First of all, it's pretty self-explanatory in terms of the lengths of the legs are. The mass of each leg is concentrated at the midway point, so 0.5 R is the location of the mass of each leg. Then there is a mass concentrated at the hip, MH, and at the torso, MT. The other thing to think about with this model is that the angles are absolute angles, meaning that they are measured with respect to the vertical. So if you look at angles Q1 and Q3 on this chart, Q1 and Q3 are positive angles. They are clockwise away from the vertical. And Q2 would be a negative angle here. It would be measured counterclockwise away from the vertical. So that means it's a negative angle. So I think that's everything about the model that's relevant. We talk about where I got that model from in a previous video. It's from a textbook. And so it was a useful model for me to use to verify or to kind of validate this fragility metric that I came up with. Okay. So the first thing we have to do is compute the center of mass position vector in terms of the joint angle vector. So the joint angle vector here is Q1, Q2, Q3. Again, Q1 being the stance leg angle, Q2 being the swing leg angle, and Q3 being the angle of the torso, again, with respect to the vertical. And so after we compute the center of mass position vector in terms of the joint angle vector, which is, well, again, what you see here on the right, this equation puts it all in terms of Q1, Q2, Q3. You might be saying, well, where are those? Well, again, S1, S2, S3, C1, C2, C3, these stand for the sine of those three angles or the cosine of those three angles. So those are what you see there in the value. And then everything else is basically those values of M, MH, MT, R, and L that you saw from earlier. Okay, so what we do is we take that center of mass position vector, which is in terms of Q1, Q2, and Q3, and then we differentiate it with respect to the joint angle vector. So what that's going to give us is, instead of a 2x1 vector, we're going to have a 2x3 matrix. And so that center of mass Jacobian is, as you see here on the screen, we've done all the derivations for you. You can easily just come up with that center of mass Jacobian based on Q1, Q2, and Q3, and all of the other parameters. So in order to come up with this matrix E, we actually just simply take the Jacobian and its transpose, multiply them together, and you get a square matrix, a 2x2. So the Jacobian is 2x3 in our case, and the transpose of the Jacobian is a 3x2. You multiply a 2x3 matrix by a 3x2 matrix, you get a 2x2 square matrix. So after that, then we can go ahead and compute the gait metrics that we talked about before. And those three gait metrics are the balance maneuverability measure, the condition number of the center of mass maneuverability matrix, and then my metric, the fragility metric. So we talked about this before, but just to recap, the balance maneuverability measure is equal to the square root of the determinant of matrix E. So we take the determinant of E, take the square root, that is the BMM. For the condition number, we take the maximum eigenvalue of E, divide that by the minimum eigenvalue of E, and that gives us the condition number. But how do we come up with this fragility metric that I'm talking about? Because it's, well, you see the equation there. It's not in terms of E yet. So we need to convert that to something that's in terms of E. So here's how we would do it. And this is for the planar case, by the way. So we're talking about a planar robot, so we're doing the planar case. If you were looking at a 3D robot, then you would need to actually get three-dimensional center of mass position and velocity vectors. So instead of that initial vector we talked about, P sub COM, being a 2x1, it would be a 3x1 in the three-dimensional case. You use that to then get a three-dimensional Jacobian. So you would differentiate that with respect to the angles, and you get a 3x3 would be that Jacobian rather than a 2x3. And then you'd multiply that Jacobian by its transpose. So 3x3 multiplied by 3x3 gives you a 3x3. So E in this case would be a 3x3 matrix rather than a 2x2 matrix for the 3D case. We're in the planar case, so we don't really have to worry about that. It actually makes the math not that much harder to go to the 3D case, but in our case, we're looking at a planar robot, so we don't have to do that little bit of extra. Okay, so if we have our E, which we just derived earlier, and we have our center of mass velocity vector, P dot, then we can compute this ellipse equation, P dot transpose multiplied by E multiplied by P dot is equal to 1. And again, P dot is the center of mass velocity, X dot, Z dot. Okay, now if we set the center of mass vertical velocity equal to 0 for this equation, then we get that X dot squared is equal to 1 divided by E11. Now that's nice because now we automatically know what our absolute value of X dot max and absolute value of X dot min is. It's just they're equal to each other. They're both equal to this 1 divided by the square root of E11. When we say E11, we're thinking about this 2x2 matrix where E11 is that first element. So it's the first row, first column of the matrix. If we do the same thing with the horizontal center of mass velocity, meaning we set X dot equal to 0 for that equation, P dot transpose E, P dot equal to 1, then we get a very similar result, except instead of the absolute value of Z dot max equal to the absolute value of Z dot min being equal to 1 divided by the square root of E11, it's actually 1 divided by the square root of E22. But you can probably see where I'm going. If you go and look at that top equation, you can see what's about to happen. You actually can now get this fragility metric by simply dividing E11 by E22 and taking the square root. So it's a really nice, really clean, simple result that if I have that 2x2 matrix E, I can simply take the two diagonal values, take the ratio between them, and take the square root, and that's my fragility metric. Okay, so let's talk about the simulation in MATLAB. I basically take a 3.5 duration number of steps. So there are about 4 steps or so that are taken over a 3.5 second interval. And we use a simulated time step of 0.01 second. And we get all the results and we'll show you the plots in a second. But the model parameters for this 3-link planar robot are given here. We use a leg mass of 5 kilograms, a hip mass of 15 kilograms, and a torso of 10 kilograms. Our leg length is 1 meter, and our torso length is 0.5 meter. Now, again, you could obviously make those much smaller or much larger as you see fit. It's a really big robot if you think of it that way, but we could obviously take that down to centimeters and grams if we wanted to do something that would be more realistic. But the masses and the lengths don't really matter. What matters is what we're going to see next, which are the plots of the posture and swing leg angle errors, the plots of stance and swing leg angles, stance and swing leg torques, and then we're going to be able to compare the 3 gait metrics and see the differences between them. Okay, so here you can see that there are 4 steps that are taken. So every time the foot touches down, we see that there is this this jolt forward. Am I recording? I don't think I'm recording. I don't think I'm recording. So I've got to go back. Let me see. Am I recording? I'm screen sharing. I am recording. Okay. So I'm recording. I forgot that I was recording. So I'll probably leave this in because I don't feel like cutting it out. But okay, so I'm recording and screen sharing everything. I just didn't want to mess up one more or have to start over. So I just don't feel like starting over. So we're just going to go with this. All right, where was I? There is a posture error and swing leg error. So what happens is basically every step that is taken, there's a slight error in the posture. There's a very specific angle that we're trying to maintain, and every time a step is taken, there's a little bit of a jolt, and that causes a slight forward motion of the torso. And when that forward motion happens, the controllers kick in and react and drive that error to zero. Similarly, there's a little bit of swing leg angle error every time a step is taken. So if you imagine that the legs actually switch positions. So if the right leg angle moves forward and then touches down, it becomes the new stance leg. And the left leg that was previously the stance leg now becomes the swing leg. And so there's a little bit of error that happens with each impact, and that's to be expected. Okay, here we see the swing and stance leg angle plots. And so for the stance leg, it starts at a negative value. So again, the stance leg starts in front of the robot, which is actually a negative angle with respect to the vertical. And then over the course of, the course of the step occurring, it increases until it gets to a maximum value of roughly 0.4, and then it becomes the swing leg. So the way to think about this is there's basically an M shape or a W shape happening for the right and left legs respectively. Here you have the stance and swing leg torques. Obviously, the swing leg, you don't have to exert as much torque to be able to move the leg because it's swinging. Whereas if you have a stance leg, you are carrying the weight of the robot. So it takes a lot more torque to do that. And so in that case, you see the difference there. Another thing to think about here is if you notice that at each impact, you'll see that one torque is at roughly 18 or 19 Newton meters, and the other one is at roughly 19 or so, negative 19. And so those switch. And so that's why you'll see, and yet, and it's hard to explain here, but basically you see that when a impact takes place, there's this large torque that needs to happen to be able to move the torso of the robot and the hip of the robot forward. So if you think about, we'll see the animation of this, but when that leg touches down, that front leg touches down, that back leg or that front leg touches down, it needs to then, that back leg is going to be picked up. It's going to need to pick up that entire robot, all of that mass and move it forward. So that's why, although the swing leg has a very minimal torque when it touches down, it then becomes the stance leg, and it needs a maximum torque, nearly negative 120 Newton meters, to begin to push that weight of the robot forward from that far position. So it makes sense that you're going to have this sudden, necessary, large torque to do that. I don't know if that makes sense. Leave a comment if it doesn't. I can explain it. Okay, so here's a comparison of the gait metrics. So there are three of them. You'll notice it says scaled for the balance maneuverability measure and for the condition number. And that's because the BMM is in a range of 0 to 0.1. So it's a very tiny range. So I multiply it by a factor to get it into a range that's closer to that 0 to 12, 0 to 15 range that we see with my fragility metric, which is a nice range. I like it at least. And so the other thing is that with the condition number, it was going up, the numbers were going as high as 1600, which is a really large number. And so I needed to multiply that by a factor to get it down into this 0 to 15, 0 to 16 range. The bottom line, though, is that the shape isn't changed by me multiplying by these factors. So you still see the shape of these metrics with respect to time as stepping is occurring. And you'll notice that there are asymptotes at each step for the BMM and for the condition number. And so if you think about it this way, when a step occurs, all of a sudden, for example, the BMM, you see it goes lower and lower and lower, and it gets down to its lowest point, and then immediately it spikes up higher. And then it goes lower, 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 spikes up higher. The condition number actually does the exact opposite. It goes up, 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 and it gets to its highest point, and then it drops down to a low point and then goes up, 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 and drops down to a low point. So pre-impact and post-impact, there is a huge gap between those metrics. But you'll notice with my fragility metric, that is not the case. With the fragility metric, there's no discontinuity there. It actually goes, it's not exactly smooth at the step, which makes sense because there is some, when the step occurs, there is some impact, but at least it's continuous. And so it's at its highest point in the middle of the step, which makes sense because when you're walking, when are you the most vulnerable? Well, when you're in the middle of that step, you've picked up one leg and you're only on one leg. If someone were to push you at that time, that's your most vulnerable position. And you see that with the fragility metric. So this next thing is a video of where I basically show a simulation of the walking. So I take the data and I actually, using MATLAB plots, I show an animation of the robot walking and in real time show the corresponding stance and swing leg angles and torques and error in the posture and swing leg, but also at the lower right, you see the three measures. So you can tell when everything spikes. So notice how right now fragility is highest, and then when it touches down, those two values of BMM and CN, they immediately, there's this huge gap, discontinuity. And so my computer just kind of froze, but you can still see this, see how it's doing this with this this simulation. So three takeaways for the fragility metric, and then there are a couple other things I want to say, and then that'll be the end of the video. So the first thing is that there's a moderate range of values. So you notice I had to scale the BMMs up and I had to scale the CN down, but our fragility metric was in that range of 0 to 15, which is a nice little range to be in, I think. I like it. The 0 to 0.1 is not bad for BMM. We could have frankly scaled everything down into that range, but 0 to 15 is just a nice range to use. So it's a moderate range of values. The second thing is that the fragility metric doesn't have those gap discontinuities that we saw with the BMM values and the CN values. And so pre-impact to post-impact, there is this huge, huge gap. It's a significant gap. And that's not something you want if you're trying to use these for some type of feedback controller. You don't want to have these huge gaps every time a step is taken. You want something that's more continuous. And we see that with the fragility metric. The third thing is that there's a correspondence with these vulnerable points in your gait cycle. And this is what we mentioned earlier, that in the middle of the gait cycle, when you're on one leg and swinging that leg through, about to, again, eventually move it in front of you and step down, that is your most vulnerable position. If someone were to push you or trip you, that is where you're most vulnerable. If you have both feet on the walking surface, that you're not nearly as vulnerable. And you see this in the fragility metric, whereas the other metrics don't really use that philosophy. That's one of the reasons why we wanted to design it that way. So where do we go from here? Well, the simulation results suggest that we could use this metric for evaluating existing gaits. So if you had a robot and you had 3 or 4 different gaits you wanted to compare, you could use this fragility metric and look at something like maybe average fragility over a gait cycle, or you could do something where you look at maximum fragility for a gait cycle, and you might make decisions on how you would design your gait based on that. That's one thing you could do. Because you can compute this online, you could actually use this as feedback that goes into a controller for bipedal gait and balance. So that might be one thing to use. I'm not kind of working on controllers right now. Most of my PhD, really all of my PhD, was about working on controllers. I want to kind of get into robot design right now. And so, and yet that's something that you could use. You could use this idea of fragility to govern how you design a robot and think about how to make design decisions based on less fragility or more fragility. So this simple metric could easily figure into that when you're thinking about how to compute E, how to consequently also compute this fragility metric. So that's all for this video. If you didn't see the previous videos, then you probably have no idea what I'm talking about. This idea of a fragility metric is something I came up with in my PhD. And so I talk about it in my thesis. But go back to videos 1 through 3, and that would give you more of a insight into what I'm talking about for this video. Thanks for watching.